Welcome back to Chem 4300. In this video, we're going to continue Chapter 19 on magnetism, angular momentum, and spin. And now we're going to turn our attention to the fine structure details that are in the hydrogen emission spectra. Now, earlier in the chapter, we saw that Schrodinger's solution to the wave equation for the hydrogen atom was successfully able to predict the positions of the Lyman and Baldwin series in the emission spectra of hydrogen. But there were finer details in the emission spectra that were not accounted for by Schrodinger's original solution. And what we know now, of course, is that there's additionally spin angular momentum, and the electron has a magnetic dipole moment that will come into play and affect the hydrogen emission spectrum. And also, Schrodinger knew at the time he wasn't using a relativistic version of the treatment, and there will be some relativistic corrections that we need to take into account in order to get the fine details correct. So let's take a look at these two corrections. So we're going to look at the relativistic correction, which is given here, that we'll derive in the notes. And also we're going to look at something called the spin-orbit interaction, the interaction of the electron's spin angular momentum with its orbital angular momentum, and it's going to take the form of this. And we'll look at these in more detail in this video. So let's start with the relativistic correction. What we know is that we started that problem using the classical kinetic energy expression of K is equal to P squared over 2m. But really, we know that as the electron moves relatively fast, we need to include relativistic effects, and that will take the form, the kinetic energy will take the form here, where here's the mass of the electron and here's the velocity of the electron, and then of course now we have the speed of light, which comes into this equation. So in the notes, we start from here and we show that we can take the original non-relativistic Hamiltonian and write a perturbation term and use static perturbation theory that this correction derived from using this kinetic energy term will give us a correction to the energy that looks like this. So what happens is this relativistic correction, which we call this is the first order correction for the nth eigenstate, is going to be equal to the unperturbed energy for the nth eigenstate squared times these terms here. So here's the mass of the electron, the speed of light squared. Here's the principal quantum number and the azimuthal quantum number. Now, one thing you'll notice is that the relativistic correction now makes the azimuthal quantum number, the orbital term here, are no longer degenerate for the same value of n. So for a given fixed value of n, the different values of L will have slightly different energies due to this relativistic correction. Now the next term we're going to look at is something called the spin-orbit interaction. It's the coupling between the electron's spin angular momentum and its orbital angular momentum. And the way we're going to describe this, and we start this out in the text and we do a more detailed derivation here. I'm just going to give you the physical picture and the final result. The way we describe it is that we know the electron is orbiting around the nucleus with the nucleus at a fixed point with the center of mass. So this is what we call the nuclear rest frame. The nucleus isn't moving and the electron is moving around the nucleus. And this electron has a magnetic dipole moment which is interacting with the charge of the nucleus as it orbits around. Now, the way to cast this problem so it makes a little bit more sense is to move into what's called the electron rest frame. So in other words, the nucleus is at rest here and the electron is moving, but if we jump onto the electron and put the electron at rest, then the nucleus will look like it's moving around the electron. So this is what we call the electron rest frame. So in this rest frame, the electron has its magnetic dipole moment and it sees a positively charged nucleus orbiting around it. So it sees a current going in this orbit around it with it sitting at the center. So this nuclear charge is going to generate a magnetic field at the nucleus because of its motion. That charge is going to make a current that's going to generate a magnetic field here. The interaction of that magnetic dipole moment of the electron with the resulting magnetic field generated by the moving nucleus is going to give us an interaction that is familiar to you from before. The magnetic dipole moment of the electron interacts with the magnetic field generated by the orbiting nucleus. Now this is all written in the electron rest frame. So what we'll do is we'll take this result and we'll transform back to the nuclear rest frame, and that's the lengthy derivation in the notes. And the result of that is that we get in the nuclear rest frame a term for the potential energy that corresponds to this spin-orbit interaction that looks like this, where it involves a parameter here, z, which looks like this, which we will calculate an expectation value of that from the wave function, and then it will involve the dot product of the orbital and spin angular momentum vectors. In this expression here for z, which is the spin-orbit coupling, this term here is the electrostatic potential at the electron. So the convention is to report something called the spin-orbit coupling constant, which is the expectation value of this term divided by the Planck's constant times the speed of light. So we just take the expectation value of this term with our hydrogen atom wave functions and divide by h c naught, and we get this number here, zeta, which Greek letter zeta here, which is called the spin-orbit coupling. Multiply it times h c naught, and you'll get an energy. Now, for the hydrogen atom, we can go ahead and evaluate with our wave functions that we derived in the last chapter, and you can get that coupling constant to be in this form here. And you can again see that we now have an n cubed dependence here in the denominator, and we also have an azimuthal quantum number dependence here. So again, we see a lifting of the degeneracy. The orbital angular momentum of the electron is no longer degenerate for the same value of n. If you change L, you now have difference in the energies. So this term here, which is called the spin-orbit coupling constant, it also involves a term here, alpha, which is a bunch of constants together, and that's called the fine structure constant. So, oh yeah, one other thing too, as I want to mention, is that this R infinity is what's called the Rydberg constant for a hydrogen-like atom. So this is an atom that has a nuclear charge that's Z instead of just Z equals 1. We can have arbitrary Z, and that's related to the Rydberg constant for the hydrogen atom by this relationship here. So for a 2p electron in a hydrogen atom, you can calculate the size of this guy, and you find that it equals about 0.24 inverse centimeters, or about 30.2 micro electron volts. Well, that's a pretty small shift on the p electrons energy level, which is about minus 3.4 electron volts. So it's small for the hydrogen emission spectrum. It's, as I said, it's a fine structure detail. But notice that this term goes to z to the fourth. So as we start looking at the spin-orbit interaction for heavier and heavier elements, this term is going to get dramatically bigger, and it's going to play a more significant role in the spectra and the electronic structure of those atoms. So if I take those two terms together, then, if I take that spin-orbit coupling and my zeroth order Hamiltonian, so if I say that this is my Hamiltonian without the spin-orbit coupling present, which we learned in the last chapter, and now I take this term and I combine these two terms, then I can get the total Hamiltonian for my system. Now, in quantum mechanics, we know that any Hermitian operator that commutes with the Hamiltonian corresponds to a physical quantity that is conserved, that's not varying in time. The expectation value is not varying in time. So we know that this term, the zeroth order Hamiltonian, which is the Hamiltonian we used in the chapter on just solving the hydrogen atom, that commutes with both the orbital angular momentum vector and it commutes with the spin angular momentum vector. So both of these quantities commute, and so that means that spin and orbital angular momentum are separately conserved if this is the only term in our hydrogen atom Hamiltonian. But in fact, actually, we have to include the spin orbit term, and we find then that the orbital angular momentum vector and the spin angular momentum vector, neither one of those commute with the total Hamiltonian, and so orbital and spin angular momentum vectors are no longer separately conserved. So they will be time dependent. They will be moving in an hydrogen atom where this spin-orbit coupling is present. Now, it's still true that the total angular momentum will be conserved. There's no torques acting on our hydrogen atom, so the total angular momentum for the hydrogen atom will stay conserved, and that will definitely commute with our total Hamiltonian and be time independent. Okay, so now let's do a first order perturbation treatment of our Hamiltonian, which consists of the Hamiltonian that we originally set up in the chapter where we solved the Schrodinger equation for the hydrogen atom. And now we're going to add to this spin-orbit coupling term. Now, before we do this perturbation theory approach, we're going to do a rearranging of this term into a form that makes it a little bit easier to do that calculation. And one thing that we know is that this term, the h naught, and this term, the spin-orbit coupling, commutes with L squared, S squared, and J, the total angular momentum vector. This is something you can check on your own. And if I take J squared, which is L plus S times L plus S, and expand out that, I get this expression, which I can then rearrange to give me L dot S given by this expression, which now I can substitute in up here to remove those vector quantities, and I can write the spin-orbit coupling entirely in terms of the vector lengths, J squared, L squared, and S squared, which are conserved. So remember, we said that L and S are not conserved vectors. They're moving as a function of time, but their lengths are staying constant. And that's reflected here. And we're going to put that into our term here so that we can do our perturbation treatment. So here's our Hamiltonian. Here's our H naught. Here's our perturbation. If we plug it into the expression, we'll take our perturbation. The first order correction is just the sandwich here with the spin orbit term here. And when we put in the wave functions for the hydrogen atom, this part right here will only act on the radial part, which ends up over here. And then these angular momentum parts will act on the angular part and the spin parts over here. And this will be that integral. And when you evaluate all of this, you end up with this expression for the first order energy correction. Now, this term, the expectation value for the spin orbit coupling, which we written in terms of this constant, spin orbit coupling constant, is given by this expression here. And so we can go ahead and rearrange this in terms of this spin orbit coupling constant and write it this way here. And this is the final form for our spin orbit coupling constant for the hydrogen atom. Okay. Now, we can look at this for s orbitals where L equals 0, S equals half. We know a total J of half. Then if you calculate that out using this expression here, you actually get a value of 0. So what you find is that the s orbitals are completely unaffected by the spin orbit coupling. And that should make perfectly good sense because an s orbital has no orbital angular momentum. So the electron is not going to couple to the orbital angular momentum if there is no orbital angular momentum. So for an s electron, then the nucleus doesn't look like it's orbiting around it at all. It's just fixed. So there is no spin orbit coupling. However, for the p orbital, for the electron in the p orbital, where L equals 1, we know that J will have values of 1 minus half and 1 plus half. So we have total J of half and 3 halves. And so we're going to have 2 energy levels we're going to looking at after we make this correction. And so this is the evaluation for the J equals 3 halves, and it comes out to be 1/2 hc naught times the spin orbit coupling constant. And this one, for J equals half, comes out to be minus hc naught times the spin orbit coupling constant. So what happens then for the unperturbed p orbital energy levels get split into the ones associated with J equals 3 halves and the ones associated with J equals 1/2. The ones with 3 halves go up in energy, by this amount, and the ones with J equals 1/2 go down in energy by that amount. So one thing we see then is that if we're going to be specifying the state of the electron in a hydrogen atom, we can't just specify the value that it has in terms of L and S, or M sub L and M sub S. We need to also specify its J state to know what its energy level is going to be. Now, we can actually rearrange this a little bit, and we can take that expression which we just had, and we can use the definition for the coupling constant in terms of, for the hydrogen atom, or the hydrogen-like atom, where Z is Z to the 4th here. Take the first order, the 0th order energy correction, and we can re-express all of that into this form here, where now it has the 0th order term here. So we have all these parameters that aren't shared in common. So we can just write it this way, lumping them all together into the 0th order energy for the nth level, and express it like this. So this makes a little bit of a simplification for the hydrogen atom in terms of its perturbed energy away from the H naught. Taking that, we can combine the relativistic part, and we can get the total energy correction, and this is all of it together. So the spin orbit and the relativistic correction together gives us this term, and you can see how nicely it is expressed in terms of the original energy eigenstate in the unperturbed case, the principal quantum numbers, the total angular momentum, J now, and this term here, which we identified earlier as the fine structure constant. Okay. So we're not going to go any further. You could actually go further here and worry about interactions of the nuclear degrees of freedom, like the magnetic moment of the nucleus and so on, and then even we're worried about the quantized electromagnetic field. But this is enough to really get us to really good agreement with some of the details in the hydrogen emission spectrum. So we're going to stop here in this video, and in the next video we're going to start looking at a way of describing these energy levels with total angular momentum and orbital and spin angular momentum, and a notation that spectroscopists like to use called term symbols.